Hello, Swatidi, can you hear me? Hello? Swatidi, are you online?
She was online then.
Yeah, she is.
Maybe for some reason. Just wait.
Okay, okay.
অর্ক মিউট করে দাও।
Hello, Swatidi and Kishore, can you hear me?
Yeah,
Yes.
I'm here. Yeah.
Okay, so since you are the chairs today, please just check your email. We have sent you the affiliations of the speakers for the sessions you're chairing.
Yeah, I saw that.
Okay. And just note all the chairs that the questions after any talk will be posted in the chat box, and you just look at them and forward them to the speaker. Thank you.
So, ma'am, should I start now?
Just one more minute. Okay, so good morning, everyone, and welcome to the next second day of Young Quantum 2020. And the first morning sessions will be chaired by Swati, and she is from Bose Institute. So, pass to Swati.
Okay. Good morning to all of you. And so, our first speaker of this session is Kishore Bharti. He is from CQT Singapore, and Kishore will be talking now on robust self-testing of quantum system by non-contextual inequalities. So, Kishore, if you are online, then you can share your slides.
Yeah. So, is it visible?
Yeah, it is visible.
Okay, awesome. So, yeah, can I start now?
Yeah, yes.
Okay. So, thanks a lot for giving me the opportunity to present my research, and because of this corona epidemic, unfortunately, we couldn't do it in person. Like it would have been more engaging, but still, like on Zoom, we are like kind of like isolated nodes of a fully connected graph. So like still we can talk, and it's I can present my research from here. Okay, so I will talk about robust self-testing of quantum systems via non-contextuality inequalities. And it's a series of works which I did with some of the colleagues which have been mentioned here. And there is some, like the paper was published last year. And then we did some follow-up work, and there is some more work like coming. Maybe in 1-2 months you will see them on archive. So the message, I mean, if I can give like a very short message, like take a home message kind of thing, it's like in Bell non-locality, people have been always interested in protocols where there's Alice and Bob, and they try to basically do device certification, self-testing, whatever, where there are two parties, Alice and Bob, and they want to together verify whether some quantum device is indeed there is some background noise, sorry. So they want to like jointly verify whether some given quantum device is actually a genuine quantum device, or somebody is bluffing. But I mean, and that led to the birth of this thing called device independence. But like if you are really in a faithfully minimalistic scenario, you cannot even trust your partner. So I mean, like, why should Alice even trust Bob? And we would need to like provide certification in a scenario where there are not two parties but just one party, like just Alice. And this makes sense because Bell non-locality is somehow like communication driven. On the other hand, the moment you want to talk about computation does, like, mostly happens locally. So you need a local self-testing scheme, a local scheme for verification. And so far in the literature, people only, because I know like Bell non-locality have been famous and all, they have been using it to basically use it for device certification and so on. And they try to even certify a pair of quantum computers. There was a paper back in 2012 by Umesh Vazirani and Raikdat. And then like series of works were done until recently when under complexity theoretic assumptions, Urmila Mahadev, basically Vazirani's student, like who is now a PI at Caltech, she managed to do certification for the case where you have a single classical device certifying a single quantum device. But still, like all these proofs which have been given in the literature, they are up to some under some complexity theoretic argument. And we need to provide guarantees under the like unconditional guarantee, and that should not be based on something like a particular problem is hard enough, or they are not in, I mean, like all the smart people tried and they failed, or whatever, as we believe for factoring. I mean, these assumptions are like solid assumptions, but still we need like guarantees based on laws of physics. Okay, so please interrupt me anywhere, like I would like to keep it very interactive kind of talk. And if anything doesn't make sense, please stop me just there. So yeah, I mean, like this is the place where I work. It's Center for Quantum Technology. And these two gentlemen, they are my mentors. This is Liang Xuan Kwek, and this is Vlatko Vedral. And it's one of the pictures of some group outings which we do with Kwek, like a very nice person. Yeah. So like I have been mostly interested in quantum foundation, computation, and artificial intelligence, and like published works at the interface of them. But in this talk, I will talk about how can ideas from quantum foundations could be used for device certification, let's say some quantum computer or something. So the goal is to basically characterize untrusted devices. And we know that, like Bell non-locality based self-testing, they can be used to characterize quantum devices. Like basically you have been given some black boxes and you press certain buttons and you collect the statistics. Now, on the basis of the statistic, if you can, without opening the devices, you can say that what is going on inside the device, then that's a very powerful statement, because I mean, in most cases, we do not have control. We are not either experimentalists, or we do not know, like how to operate the devices, the inner working of the devices. What we only have control over is that we can press certain buttons and see what output it's generated. I mean, an example I can give you, like, if somebody gives you a phone and tells you that, it's an iPhone, but uh, it could be possible that, inside is basically some Samsung phone or whatever. Now, without opening the iPhone, how would without opening the phone, how would you know that it's indeed an iPhone, and or like, and somebody is not bluffing with you? So in quantum regime, this really becomes an important problem, because often at times we do not know in the like whether the underlying system is genuinely quantum, or the phenomena is being simulated classically, or like or something else is happening. So without opening the device, if you can certify what is inside the device, then that's a powerful statement, and that's basically the statement of self-testing. But if you think about Bell non-locality, it's a particular case of some phenomena called contextuality. And where this notion of context, I will tell what context means, like I will define it later, is basically provided by a space-like separation of the parties involved. So you have, Alice and Bob, like, separated. And the tensor structure basically allows you to, provides you the context. But you need not have a tensor structure always to generate context. I mean, you can have a single Hilbert space, and there you could have observables which commute among themselves, and like, some of them do not commute among themselves. So somehow this context is related to compatibility or commutation, if you think about. No, what we say that because Bell non-locality is a special case of contextuality, is it possible to extend the idea of Bell self-testing to non-Bell contextuality scenario? I mean, the scenario where there are not two parties. I mean, like multi-party is still Bell scenario, like a single party, like, the case where somebody has some device and they want to know whether the device is actually a quantum device and it's performing what it is supposed to perform or not. Okay, so like in Bell scenario, for example, like Mayers and Yao, back in early 2000, basically they said that if you have some inequality, like such a CHSH inequality, and if you achieve the maximum quantum violation of the inequality, let's say 2√2, under the assumption that Alice and Bob are not communicating to each other, basically a space like separated, and like then the underlying, and if the statistics has been generated via some quantum process, then the underlying quantum state must be a maximally entangled state, and the measurement settings must be what you see on the slide, up to some local isometry. So you can rotate them, like by applying some local isometry or something. Now this is a powerful statement, because you just look at the violation of the inequality and you see that if you get 2√2, then basically you are giving guarantee about what is inside the box. And yeah, and then this basically like helped people develop, like schemes about many certification schemes in the community, and like has been very rigorously explored in the literature. And if you really look at Bell inequality, what it is basically, like it's some hyperplane. I mean, by Bell inequality, I mean, the linear inequality, which we mostly talk about. You can also have non-linear Bell inequality, which have been recently studied in network scenario. Probably, I think Nicolas Gisson will talk about that in one of the keynote sessions. So let's focus on the case where, like you have some linear Bell inequality, some hyperplane, and you have some basically some probability distributions, like a family of probability distributions, and you have some coefficients in front of them, and basically you say that this hyperplane, like like basically you have some bound, and overall you have some half space basically. And you say that if whatever in the experiment is being generated is basically satisfy the assumption of locality and realism, whatever, then I will not violate this bound. But in quantum theory, what happens that you these probabilities that you generate here, in quantum theory, you generate them via bonds. I mean, you explain them via bonds rule. And given if you take some quantum state psi, which belongs to like the joint space of Alice and Bob, then basically you can achieve some other quantum value, some other value of this expression, which is BQ, and this BQ can be often greater than equal to BL. So BL is the local bound, and this BQ is basically the quantum bound. So you can think about in the case of CHSS, this is 2 and this is 2 root 2. And basically self-testing says that the moment you achieve, the moment you basically achieve this value BQ, I mean, it's like when you touch this number, you touch God. I mean, like, I mean metaphorically. So the moment you have this number in your statistics, it gives guarantee that the underlying measurement settings and the state must be some particular quantum state and some particular collection of measurement setting. So you have some Hilbert space A, Hilbert space B, and some quantum state psi, and some like POBMs A, POBMs by Bob, like B. Like basically it says that if you can consider them projectors, like no need to think about POBMs, like you can always dilate and all. So what this self-testing statement says that if you have one configuration which achieves, let's say, like if in case you achieved the maximum quantum violation, then no matter which configuration is there, it's related to some ideal configuration via some local isometry. So you have some isometry V equal to VA tensor VB, and it basically maps one configuration to another. So basically now you are able to pinpoint and say that what is going on inside the device under some irrelevant degrees of freedom, like local isometry or something. Okay, and but in experiments you do not achieve basically 2 root 2. Let's say in the case of Bell scenario, you achieve something like 2 root 2 minus epsilon. And to really make these protocols, like I'm unable to experimental inaccurate, like experimental noise and all. You need to make the protocol robust, which says that instead of BQ, which is the maximum quantum value, the quantum violation, if instead of BQ, if you achieve BQ minus epsilon, which is like instead of 2 root 2, if you achieve 2 root 2 minus epsilon, then still you should be able to give guarantees about what is going on inside your device up to some error. So whatever, like if instead of optimal violation, if you achieve epsilon suboptimal violation, then you should be able to say that basically the whatever is going on inside the device is close to the ideal configuration in some norm up to order epsilon r. So this will be called epsilon r robust self-testing. I mean, Bell self-testing mostly is epsilon half self-testing, like the value of r is often half. Okay, so we have talked about self-testing in the Bell scenario, talked about Bell non-locality, I mean Bell inequality, and then what does Bell non-locality kind of mean. Now I will change gears and like talk about contextuality a bit. So contextuality, you can think about a context, the meaning of context as a set of compatible observables. So you have, let's say, observable A, B, and C. Now, let's say that A, for the moment, think about like them as like commuting observables. So like, I mean, if you think about the pure like projectors and think that they kind of commute. So if they commute, they will become compatible for projectors. So let's say you have observables A, B, and C. And A and B, basically A and B are compatible, A and C are compatible, but this compatibility relation in quantum mechanics is not transitive. What that means is that if A and B, let's say, commute, and A and C commute, that does not necessarily mean that B and C will commute. So you can create trivial examples where you can say see that this does not happen. So basically now this observable A belongs to two contexts, like context 1 where it is measured together with B, context B where context 2 where it is measured together with C. You can think about as it happens in the Bell scenario, like all the Alice observables are compatible with Bob observables, like but not among themselves. And any given observable is compatible with belongs in two contexts for Bob's choice of measurement. Now we say that given a theory, if the value assigned to the observable depends on the context in which you are measuring it, then the theory will be called non-contextual. Otherwise, you will call it contextual. And there are proofs that quantum mechanics is a contextual theory, and you can prove it whatever. But we are not interested in like the philosophy and all those things. Like we can talk about ontology and what does contextuality mean and all those things, and these things are interesting. But we want to move towards looking at it more from the mathematical perspective, and want to say some statement which can have practical relevance. So for that, we start looking at this thing called this graph, which was developed by my collaborator, like Cabello and Severini and Winter. And basically this approach came in 2014. It came on archive much before, like it was published in the journal in 2014. So it says that it's an approach to look at basically a contextuality experiment, or any experiment you can think about in like via graph theoretic notions. So in any experiment, what happens that you measure and you have some preparation, and for that preparation you have some choice of measurement and you get some output. So the choice of measurement and the output together, they constitute an event. So let's say you have a set of events E1 to En. Now we will say that two events, they are exclusive if they correspond to same measurement but different outcomes. So that's like, I ask a question, and if you give me different answer, like 2 times. So basically I will say that the case 1 is, the event 1 is mutually exclusive to event 2. So now you have some kind of a relationship. So basically you have some events which can be thought of nodes, and there is certain relation between events which is like mutual exclusivity. So what you can do, that you can represent these events by a node of a graph, and whichever node is let's say whichever event is mutually exclusive, you can connect them via some edge. So for example, here I have events E1 to E5, and if they are cyclically mutually exclusive, then I will denote them by I will represent them via this graph, the pentagon. You can think about the CHSH basically as this graph, like basically the 8 probabilities that occur in CHSH. You can represent them via this graph, which is circulate graph 1,4. And the beauty of this graph theoretic notion is that you can talk about like all those the classical set, quantum set, or the super quantum set. They all correspond to basically well-defined objects from graph theory. So then it becomes a problem in quantum foundation. Like you can translate a problem in quantum foundations to a problem in combinatorial optimization, and then you can solve it there and come back here and make statements. So basically what you have a set of nodes, and basically you assign probability to them, and if they are exclusive, then you say that Pi plus Pj is less than equal to 1. What it says that if event I can happen, then event J cannot happen. I mean, that's what mutual exclusivity means. Now the set of non-contextual behaviors, the behaviors for which you can say that you cannot observe contextuality, it makes some kind of object. I mean, which you can think about, like a generalization of polyhedron or something. It makes a polytope. And the facets, the hyperplanes of that polytope, they are basically non-contextuality inequality. So for example, you can find the case, you can look at this and find the CHSH inequality. Similarly, you can take the polytope corresponding to this graph and get the KCBS inequality. And the bound on the inequality, the classical bound, basically correspond to some number, which is called the independence number of the graph. The quantum bound in the commutative structure corresponds to something called Lovász theta number, which is something which you can compute using a single semi-definite program, which is a family, which is a class of efficiently computable programs. So what you say that you have so you say that the behavior is a quantum behavior if and the behavior is basically a set of probabilities basically. So you say that the behavior is a quantum behavior if you can have some quantum description of the preparation and some projectors acting on the Hilbert space like H such that you can explain your pi as trace of rho pi I, where trace of pi I pi j equal to 0 if I is mutually exclusive to j. So basically you're saying that whatever is like mutually exclusive, for that I will assign orthogonal projector. Okay, and BQG basically that is the set of quantum behaviors. BQC is basically the quantum value corresponding to the non-contextuality inequality. So now we will say that similar to the Bell case, like in the Bell case, we had this BQ and we had this local value BL. In the contextuality scenario, which is like a more general, we have this quantum value, which is BQC. And we will make similar statement with respect to self-testing because like we can formulate the self-testing statement as an optimization program. What it is saying that you are basically looking at the maximum value of some linear expression, and because it's a convex set, the maximum value will occur at the at the boundary, and if that point turns out to be like unique point or something, then you can give guarantees about what preparation and measurement setting is giving you that particular behavior in the set of quantum behaviors. So I mean we looked at the self-testing phenomena as an optimization program, and we said that why not apply to single party scenario. And again we come up with a similar definition for robust self-testing in a single party scenario, where we say that you have some preparation and measurement settings, like so I equal to 0 is the preparation and the rest of them are the measurements. And in case you achieve the maximum quantum violation of the non-contextuality inequality, then whatever other preparation is which can achieve this value, it must be related to the original preparation up to some isometry. Notice that I'm not talking about local isometry here, because I am not like saying that there is Alice and Bob and whatever. I'm talking about single party scenario. So I'm saying that there is a isometry V, global isometry, which acts on all of your UI, and it maps that to UI prime, like the same isometry. So you can basically rotate, like so it's like you have some configuration and you can rotate it, and in some you can in some sense, and you will get whatever other configuration, and these configurations can only give you this bound BQC. Also, this is robust in the sense that if you are epsilon suboptimal, then you should be able to give some guarantees about what's going on inside the device. Like you can bound the fidelity up to some epsilon r in some norm, whatever. We tried Frobenius norm. Okay, so I mean, so what we say that earlier people have been like publishing papers on self-testing, like there have been paper like self-testing this, self-testing that. What we are saying that we kind of made the self-testing procedure algorithmic, and there is a paper that I'm writing recently with Masahito Hayashi and Adan Cavello, which will come in let's say 1 month or something, where we have recovered all the Bell self-testing, whatever Bell, some of the Bell self-testing schemes within our framework, like in the algorithmic framework.
So 5 minutes are left.
Oh, sorry. Okay. So I will rush a bit. So please we can talk later also, like if you are interested, but I think I was slow, okay. So So what you can do, that you can convert the self-testing scheme, like the process of probing self-testing as something like an optimization program, which is a semi-definite program, and you can look at its dual, and by providing some dual certificate, you can give guarantees about the uniqueness of the primal optimal. And yeah, you can prove some theorems or whatever regarding that, and it's a very algorithmic technique where you can you can basically move in a graph framework, and starting from the inequality, you can prove the robust self-testing via following this scheme. And we proved this scheme to generalize KCBS inequality, all of them. We proved it to like the odd cycle complements. We also like recently performed some experimental self-testing with the USTC group. I mean, that paper will be also coming in, I think, a month or something. And then we also like recovered self-testing for the CHSS scenario, Marmin, and then I think yeah, like all chained Bell inequality, and we tackle this problem of local versus global isometry. There are many open questions, but yeah, in future, which one can look at, and you can look at like these papers where like they have been mentioned. But if you can think about the key like take home message, it will be basically saying that for Bell non-locality has been good for communication. For computation, we should not get obsessed with Bell non-locality. We should look at contextuality, which can work in a single party scenario, because computation happens locally, unlike communication. And all our certification schemes should basically harness the power of contextuality, which like occurs in single party scenario also. And all of this framework is very like algorithmic, and you can just follow the procedure algorithmically, and starting from the inequality, you can prove robust self-testing. And along the way, you have to play some mathematical tricks. But yeah, it's so basically the message is that one need not publish like papers after papers on self-testing. This single scheme will like take care of most of the cases. Yeah. So with that, I kind of stop my yeah, like my talk is over. Once again, I thank like the organizers of the conference, and yeah, we have been managed to basically organize it during the difficult times. For that, I really thank you. I mean, genuinely.
Thank you, Kishore, for a wonderful talk. And there are some questions. The
Yeah.
first question is.
So can I see myself the questions in the chat box or somewhere?
Yes, it is in the chat box.
Let me see the chat box. Yeah. Okay.
So first question is, this idea can be extended to any locality inequality or non-linear or linear, non-linear, or two-party and multi-party, etc. or for randomness generation through sequential measurement on a single party.
See, like I mean, like what I gave you an like an algorithmic procedure. So you can use it, for example, in a multi-party case or whatever. You can like, for example, we recover the CHSH or Marmin self-testing, or like yeah, like or chained Bell inequality self-testing. So whatever is there in the Bell scenario, almost everything can be recovered in this scheme. In the single party scenario where Bell non-locality does not work, still you can use it to for example, in the KCBS case, you can use it to like say something. Yeah, like for example, you can prove the robustness and the self-testing.
And second question is from Aditi ma'am. When you said about algorithm, are you talking about semi-definite programming? And I mean that.
Yeah, I can read it. So sorry. I mean, yeah. So basically, this yeah. So this by algorithm, I mean like I should. Maybe I can like move the screen like. Can you see this thing here? Like so this is the algorithm. I mean, I could not present because of the lack of the time, but I mean, semi-definite program is involved here and there, like when we are proving the error bounds, and like when we are proving like uniqueness by some dual certificate and all. But by algorithm, I mean that you start with an inequality, look at the corresponding exclusivity graph, and then look at the corresponding lowest theta number, then the corresponding the quantum set, then you prove the uniqueness of this X matrix that you have here, and then optimal X, and then you prove some error bound by SDPs. And if that happens, then basically your non-contextuality inequality has admitted robust self-testing. So in that sense, it's algorithmic, like you have to just follow this prescription. And along the way, you will use semi-definite programs also, like to say something about, like certification and something. Yeah.
It's a method, actually, systematic method to prove any self-testing. That is what you're proposing.
Yeah. So like by algorithm, I mean in a set of rules using which you can. So your desired task is basically getting proving self-testing result about. So you can think of more as like some certification protocol or certification algorithm. Yeah.
Okay, and next question is from Gautam Sharma.
Uh-huh.
Can you please mention in brief how your self-testing scheme is robust to noise?
Okay. So I mean, we proved that in the so what happens that in the experiment you will not achieve let's say for 2√2 you will achieve 2√2 minus epsilon, or in the case of Kc-based inequality you will not achieve √5, you will achieve the √5 minus epsilon. So what you can do that again using some error bound analysis for SDPs, you can prove that instead though we proved for KCBS and others, but our robustness scheme is general. Because we proved using SDPs, which was blind of what inequality you are talking about. So no matter which inequality for which you have to basically show it up to here only. And because our proof is general, and if you have proved self-testing, then our proof automatically guarantees robustness. So you do not need to prove robustness in future. It's guaranteed by our error bound analysis.
Okay, and next question is from Shiladitya. How robustness differ from self-testing based on Bell test and based on contextuality?
Yeah, so okay, it's a very nice question. So for example, if for example, as I mentioned, you will see the work coming next month sometime, where basically we recover Bell-based self-testing. And whatever is there in Bell, that is present in our framework also, because we are not distinguishing between Bell or like single party or many party. But if you think about robustness, if your question is about multi-party robustness versus single party robustness, Bell self-testing obviously will not work in the single party case. But if you compare at the level of robustness, both of them are epsilon half robust. What it means that if instead of the quantum value, you achieve quantum value minus epsilon, then your measurement settings and state, they will be close in some norm up to epsilon half. Yeah, up to some constant. Yeah, some multiplicative constant.
And next question is from Professor Ujjwal Sen, that what is it that differentiates maximal violation?
What is it that different maximal violation?
Maximal violation and non-maximal violation, that the formers are unitarily connected and the letters are not. Is it that the maximum violation set is curved while the inequalities are flat?
What is the difference with maximal violation and non-maximal violation, that are formals are entirely? Okay. So maximum violation that happens, at the boundary of the quantum set, right? It's a convex set, and you are maximizing some linear expression. So we are always interested in linear expressions, and because SDPs and all, they will work in the case where you linear Bell inequalities. But in the network and something, we cannot make statements because they are the quantum set, first of all, is not well characterized, and the inequalities are also non-linear. But assuming the case where like the regular case of CHSH or whatever, mostly we studied pre-2010 era, there you have a convex set and you have a linear expression, and the maximum violation basically the place where it occurs, it's basically an extreme point. So it should be carved or something, like, I mean, so that you cannot write that as convex combination of two other points or something. Yeah, so it should be a bit curved. While, yeah, but on the other hand, if you are inside, then because the set is convex, you can, like, use you can explain them by, like a convex combination of two other points. So the uniqueness of the set somehow, uniqueness of the point in the set is somehow lost when you are inside and not at the boundary. Yeah.
Okay. Another question is from Nitika Shekharwade.
Yeah.
You mentioned that non-locality is a special case of contextuality. Can you
Mhm.
recover the non-locality self-testing cases from contextual self-testing cases?
Yeah, this is a very good question. I mean, like, non-locality is a special case of contextuality. I meant in the case of, like, by the definition of context, like, the way you define context in the case of non-locality is via space, like, like putting the tensor structure. And if you think about, like the framework that we are using, it's basically the commuting structure framework. And in many cases, like, like we have recovered, like you will see some work, I mean, as I mentioned, like, we have recovered CHSH, Marmin. I mean, in fact, we managed to prove self-testing for a case where Bell scenario, Bell community didn't know that the self-testing existed there. So our framework manages to recover most of the uh, uh, self-testing which is in the Bell literature, uh, by following our, this procedure. And the only trouble, like, there is that one of the trouble there is that, like, instead of global isometry, you have to talk about something called, like, yeah, this the local isometry. So if you go somewhere, like, I mean, in the case of Bell, basically, in Bell scenario, we say that, like, our V should be, like, VA tensor VB. But in the case of contextuality, we say that there is a single V, and we do not talk about tensor structure. So somehow in the commuting structure, you have to embed the tensor structure, and the geometry of the quantum set plays an important role. So if they somehow touch, and the maximum quantum violation is equal to lowest theta number, then in those cases you can work in the commuting structure and recover the results of the tensor structure. Yeah.
Okay, thank you, Kishore.
Thanks a lot.
And okay, now we move to our next speaker, um, Prabha Ghoshal. Arkav, are you online?
Yes,
Arkav,
yes,
okay.
yes.
Arkav is from Bose Institute, Kolkata, and he will discuss on facets of bipartite non-locality, sharing by multipartite observer by sequential measurement. So you can share the screen.
Am I audible?
Yes, you are audible.
Okay. Okay. So may I start?
Yes. So you have 25 minutes for the talk and 5 minutes
Hello.
for the yeah, you can start.
Okay. So, so at first, I'm very much thankful to Young Quantum 2020 for giving me this opportunity to present one of my research work. So it's on the topic of bipartite non-locality sharing by multiple observers via sequential measurement. Currently, I'm doing PhD from India, and my supervisor is Professor Shomsubra Gangotpadhyay. So here is my contents. So at first, I will briefly discuss about quantum correlations, Bell non-locality, then the properties of Bell non-locality, and next, the interesting property is the monogamy condition. And when we go beyond monogamy condition, then simultaneous violation occurs, then I will try to figure out our motivation and then the results. Okay. No, this paper actually published in Physical Review A journal in 2018, and my collaborators were Dorshi Das, Shourodip Shashmal, Shiladitya Mal, and A.S. Mujumdar. Okay. So quantum correlations, to figure out consider two space-like objects, space-like labs. Space-like means one lab cannot signal the other and vice versa. In that particular scenario, two labs are sharing some bipartite state, uh, and they are trying to figure out that the shared correlation is quantum or not. Now, quantum correlation which cannot be simulable classically using any classical local model or any local realism. So there are different types of correlations like Bell non-locality, steering, entanglement, all have different perspectives. For example, entanglement. One cannot create entanglement using local operation and classical communication. So now in case of steering, steering has different local model. And for Bell, so Bell in case of Bell non-locality is in with local realism. That means if there are two space-like objects uh, and they are bounded by no signaling condition, then any local realistic model cannot explain Bell non-local states. So then we get some kind of violation. Now let us talk about what is Bell non-locality, since we are bothered with this red region only. So it is the strongest type of physical correlation. So Bell non-locality, let us consider a bipartite qubit state shared between Alice and Bob, where Alice cannot signal Bob. So those are basically space-like objects. So both labs have different measurement devices or measurement apparatus, where Alice chooses some measurement apparatus from some set A, measurement set A, and Bob chooses some measurement apparatus from some set M with some outcomes A and B. Now, if this type of correlation associated with rho AB is classically simulable, then there will exist a local hidden variable model where this is basically a joint probability and this correlation is contained in this probability distribution. Okay, so this probability is basically A gets outcome small a and Bob gets outcome small b, such that Alice measures in A and Bob measures in B, such that they are sharing some bipartite state rho AB. If this can be written as a product of the marginal probabilities with some p lambda as a convex combination. So p lambda is basically a hidden variable. So if this equality holds, then one can say that basically not not non-local correlations. These are basically local correlations or classical Bell local states. Now, to detect this Bell non-locality, what one must construct, since these actually forms a polytope structure. So polytope means a compact set, Euclidean compact set with a finite number of extreme points. So we have to construct the polytope structure. So these are basically an n settings inequality, where n settings mean Bob and Alice have n settings apparatus, and these alpha is basically a coefficient which can take discrete value +1 or -1, and this is bounded by some local realist bound. So depending on the type of inequality. So for a simplest case scenario, for a two setting scenario, this is the well-known inequality occurs, that is a Bell CHSH inequality, where Alice has two settings A1 and A2 and Bob has two settings B1 and B2, and this is always bounded by 2. So classically one can achieve at most the bound 2. Now what happens if the state is rho AB is maximally entangled or a singlet state? In case of a singlet state, one can get this expectation value AI Bj, where I and J are basically settings. the correlation functions. This basically becomes minus cos theta for maximally entangled states. That is anti-correlation. Now, for some specific choice of theta, for example, pi by 4, when Alice chooses measurement settings in two orthogonal direction x and y, and Bob chooses two orthogonal direction x plus y by root 2 and x minus y by root 2. In that case, a maximal violation occurs, that is 2 root 2. So obviously this inequality actually violates, so it is a maximal violation, or rho AB demonstrates Bell non-locality. Now, there are two properties of Bell non-local states. The first property that is, it always signaling principle, where I have told earlier that Alice and Bob are basically two objects where one cannot signal the other. Now, in that case, mathematically, no signaling condition is meant by this type of conditional probability, where if I take the marginal sum over the outcome B, then I will get this type of conditional probability. This actually signifies that Alice gets some outcome A such that Alice measures at some measure, and Bob chooses some settings B. It will not depend on the Bob settings. In Bob is like separated from Alice, and Alice cannot signal Bob. So this is basically a no signaling condition. The next condition is the monogamy condition. Monogamy is also well established in tang. So in this case, the Bell non-locality also incorporates with monogamous. For example, consider three-party. Sorry.
Orko.
Yes.
Yeah, maybe you can
Yes,
off the video, because it's actually sometimes your voice is a bit stuck, so it will be a bit smooth.
Okay.
And later on you can on, because
Yes.
oh sorry, you have to go to
Yes. Okay.
down. There is a stop video in the Zoom. There is
Where is it actually?
it's down in the share screen, and of this option there is a mute button next to mute button.
You have to stop sharing
Okay.
first and then go back to Zoom.
Oh, acha. That's bad actually.
Okay. So I close my video. So
Yeah, you can now share.
okay. Is the sound clear, ma'am?
Yes, it is clear now.
Okay. Okay. So consider a three-party case where there is A, B, and C, where A has only one umbrella, and the umbrella can be only shared by with either B or either C. But simultaneously, both B and C cannot share umbrella with A. And monogamy condition is just like that, where this is maintained by this type of inequality, where if there are three-party Alice, Bob, and Charlie, then this equality always holds. If this equality is violated, that means no signaling condition is violated. That means either Alice is signaling Bob or Bob is signaling Charlie. So now consider a problem that if we go beyond monogamy condition, is it possible that both B and C can share umbrella with A? That means both B and C can demonstrate a Bell violation with A. Is it possible if we go beyond monogamy condition? In the paper, Art Silva et al., they have shown that two Bobs can sequentially violate Bell CHSH inequality in a two-setting scenario, where they are considered that there is a single Alice and multiple bobs, at least two bobs. Uh, those bobs are basically time-like separated, and Alice is basically space-like separated from the bobs. So Alice cannot signal Bob, but Bob one can signal Bob two. In that particular scenario, if Alice performs some projective and Bob's performs some kind of weak measurement. First, Bob one performs some weak measurement, and then he passes his qubit to Bob two, and Bob two next performs some kind of weak measurement. In that particular scenario, they demonstrate that both Bobs can actually demonstrate Bell violation with the Alice. Now, uh, why they have to perform weak measurement? Since if Bob one performs projective measurement, then the correlation will be lost in the next round. So this is basically the optimal measurement system. A measurement device can be thought as a pointer state, where q is basically a continuous variable. This is basically a position vector. So it varies from minus infinity to plus infinity. Now this measurement device or the pointer state actually interacts with the quantum system. For example, suppose the quantum system is in a pure state and becomes entangled. So after the interaction, the quantum system looks like this, where F is basically the quality factor. This basically measures how much I disturb the quantum system, and G basically measures how much I entangle the quantum system. So there always remains a trade-off between these two quantifiers F and G, and the optimal, they have estimated an optimal condition where F square plus G square is equal to 1, where so the pointer state which satisfies this optimal condition will be known as the optimal pointer state. So next, Kamal and D. Home, they have published papers in Mathematics 2016. They have shown that the weak measurements can be thought as a POVM measurements. So they construct a POVM to satisfy this optimality condition, where G is basically the precision of measurement and F is basically the quality factor. Now they consider a two outcome measurement, and this lambda is basically the strength parameter. Now they also showed that at most two bobs can violate Bell non-locality with a single Alice if this type of measurement is performed by Bob 1 and then next to Bob 2. So Bob 3 will not demonstrate any kind of violation in a two-setting scenario, where each party is measuring in a two-setting scenario. So far, what have we learned? That in a 2-to-2 scenario, that means that means two party, two outcome and two dichotomic settings measurement scenario, at most two ops can simultaneously violate the Bell CHSH inequality. Now what will happen? This comes the latter question. If we increase the number of settings, then what will happen? Now, as we increase the number of settings, it may occur that the number of pop may be increased or not. Now, this was a interesting question, which was our motivation. Uh, so let us consider this scenario where there is an Alice and there are multiple pops, and Alice is sharing some qubit with pop 1. So initial state is obviously shows maximal violation. If Bob1 performs some projective measurement and Alice performs some projective measurement, that it demonstrates a maximal violation. Now, if Bob1 performs the optimal POVM and passes the qubit to Bob2, then Bob2 again performs the optimal POVM, and the last Bob actually performs a projective measurement. So in that particular scenario, uh, it can occur that Bob n up to Bob n, where n is some arbitrary number, get some violation with single Alice for some settings number m. Now let us start with the singlet state between Alice and Bob 1. So Alice is performing projective measurement. Okay, so these are basically dichotomic measurement with two outcomes. And for example, there are settings are in a number of settings, and an unsharp measurement. This is basically the measurement what Siladitya constructed. These lambda is basically the sharpness parameter of ith bob, and these mu are the settings number of bobs. So the measurement direction can be written like this, and what we actually
Hello. Oh,
okay, okay.
Marco got disconnected, I guess.
He's still there, but I think the share screen got off.
No, I think he is now disconnected. That's why he's.
Yeah, the voice is also not audible.
Yeah.
No, he's there. He's there.
Actually, my internet connection is very low. Sorry, sorry for the.
No, it's okay. You continue.
So in a in a 242 scenario also, for a 4 setting scenario, we found the same thing, that at most 2 bobs is violating inequality with a single Alice, not much than not 3 bobs, only 2 bobs. So up to 4 settings we observe. Then we since we do not get any advantage, so we didn't further study. So we studied up to 4th settings. Now next we study for a non-maximally entangled states. Now non-maximally entangled states can be written like A00 plus B11. That means if the initial state shared between Alice and Bob 1 is taken as a non-maximally entangled state. Now one may ask that what is the advantage of taking a non-maximally entangled state, since it is a less resource state than a maximally entangled state. Now the interesting
Arkav, you are left with 4 minutes. Okay.
that there exists a minimum concurrence, a minimum permissible concurrence, below which any local realist inequality doesn't show any violation. So different local realist inequalities has different permissible C minimum, that means minimum concurrence, which also signifies their robustness. So what if we found that the Bell CHSH, that means 2 settings inequality, is the more robust, and the minimum concurrence is 0.76, and the other local realist inequalities has minimum permissible concurrence obviously greater than 0.76. So it was an interesting result. And if we start with a mixed state, so mixed state is more practical, since noise is actually unavoidable. And we also start with the Warner state. The importance of studying Warner state, that it belongs to a single parameter family and easy to calculate the concurrence, and where the concurrence is proportional to the entangled fraction of these Warner state. Now for the Warner type of state, we also found the same thing, that the Bell CHSH, for the Bell CHSH violation, the minimum concurrence required, minimum singlet fraction will be 0.89. So that is proportional to the permissible concurrence also, or the permissible entanglement. Now let us come to the summary. That in a 2-to-2 scenario, at most 2 bobs can demonstrate Bell non-locality with a single Alice, going beyond the monogamy restriction. And considering the higher settings, non-local inequalities, we found that at most 2 bobs can violate Bell non-locality with a single Alice. Which type of non-locality is more robust? That we found that a 2-to setting scenario is the more robust scenario than the others. Now there are some limitation of our work. We gave actually a conjecture that since we didn't go beyond 4 settings, but there can exist arbitrarily large number of settings. But in that case, it will be a mathematically hard problem, since the facets actually increases its size, and there exists in number of inequalities. So we just gave a conjecture that at most 2 will violate in number of settings. But later, Sheno et al. Proven that in a follow-up paper, they proven that the nearly infinite settings. This is basically they didn't prove this statement, but they prove it numerically that nearly infinite number of settings, at most 5 pops can violate with a single Alice if they share a Warner state. If they start with a Warner state. A more general result was shown by P.J. Brown later, and they showed that nearly infinite number of bobs can violate or demonstrate Bell non-locality with a single Alice in only 2-2-2 scenario. But the assumption was more general assumption than ours. They actually considered a scenario where the measurement settings, where the measurement directions have different type of sharpness parameters, where we put the extra assumption that at every measurement direction bob will have same sharpness parameter, but this was an extra assumption. If this assumption is relaxed, then it may occur that nearly infinite number of pop and unbounded number of pop can violate or demonstrate Bell non-locality with a single Alice. So thank you. Uh,
Thanks, Orko, for this informative talk. So there is a question from Professor Aditi Shende that what are the Bell inequalities that you took when you increase the number of setting? And now in case of
yes.
sequential measurements, after measurement, we get a Warner state. We know that you can't increase the violation by increasing setting. So why do you expect to have more than 2 bulbs?
So actually, we use these type of inequalities for a 3 settings scenario. That is chain 3 settings Gaussian inequality G3, and this type of inequality. And for this case, we get this number of pops demonstrating Bell non-locality. And for 4 settings, sorry, this is written wrong. This will be Bell non-locality. And for this case, 4 settings, we use these type of inequalities, chain 4 settings, G4, Gaussian inequality, DZC. These are basically, we took the reference from the definition is written in these references. So, yeah. Okay. Sorry.
Yes, it is okay. So we can,
Okay.
yeah.
Okay. Thank you.
And there is another question from YouTube, but I think we can take it later. So from quickly, if you can take it. In a Bell scenario, the devices are uncharacterized. So in such a case, is it even possible to apply unsharp measurements? So this question is from Sashankta from YouTube.
Yes, in that case also, if we want to perform any sequential type of measurement, those unsharp measurements are basically optimal measurements. So one can actually perform with that measurement also. Uh, Actually didn't get that question.
Okay. And there is another question that how you calculate the evolved state for second bob and after bob one has performed unsharp measurements.
Sorry.
Okay.
Actually, I cannot see the chat box here. So, uh,
So
can you
wait,
please kindly repeat the question?
okay. How you calculate the evolved state for second bob after bob one has performed unsharp measurement?
How to calculate the evolved state? So, it is
It
basically the evolved state is basically we do the transformation. I mean, L is performing some projective
no,
measurement. Uh, at first, Bob one is performing some unsharp measurement, and
yes.
then he is passing to Bob 2, and then Bob 2 is again performing projective measurement, and finally when we are calculating the statistics, then Ali is actually we are thinking that Ali is actually performing some projective measurement, and we simultaneously calculating the statistics between Alice and Bob 1 and then Alice and Bob 2, and then we are showing that it's violating the CHSH inequality or not. So these in this type of evolvement we are done here.
Okay. Okay, thank you, Arko, for this informative talk. Now we move to our next speaker, that is Soham Pal from Aizer Pune. And Soham, are you connected?
Yeah, can you hear me?
Yeah. So
Uh,
you can.
so yeah, I'll share my screen. I think I'll keep my video off so the connectivity stays good, I guess.
But it is not shared yet.
No, I will share. I'm just saying that I'll
Okay.
share the
Okay.
screen, but I'll keep my
Okay.
video off so that the connectivity is fine.
Okay.
So is that visible now?
Yeah. It's,
I see. So first of all, thank you all the organizers for organizing this online, even in the presence of this pandemic. It's really good to come together, all the physics domain people, and discuss even in this quarantine time. So anyways, I'll give my talk on quantum correlation and quantum thermodynamics using NMR. So we have done the experiments in NMR, and basically what we try to do is we see the thermodynamic processes and various phenomena happening at quantum level, and also see how correlation play a role in it experimentally. So please, I understand that people can post their questions on the chat box, but if someone has some questions, they can stop me in between as well, if the organizers allow that. So that will be fine with me. So anyways, so let's start. So I'll start with a very brief introduction into what a Szilard engine is, because I think it gives a very good intuition about how information plays a role in thermodynamics. Followed by, I'll give a brief introduction into NMR and how we use NMR nuclear spins as qubits. And then I'll move on to the various projects. So to start with Szilard engine. So suppose you take a box which is maintained at a constant temperature T, and you have a gas particle, ideal gas particle inside, which is bouncing around. And suddenly a demon, an all-knowing demon, introduces a movable wall, and which is weightless, let's suppose, in the middle of this box. And the particle gets trapped in one of the sides. And then what he does is he attaches a pulley and tries to extract differential work from it. So you can calculate the work, and what the work you will see, you can extract as kPt ln of. Now the question is, where is this work coming from? Because you know from thermodynamics that you cannot extract the work from a single temperature. You need a source as well as a sink in order to extract the work from it, to use heat to extract work. So where is this work coming from? So let's see what we are missing. So again, the particle was inside the box. The demon introduced the wall, all right. But at this point, he doesn't know which side the particle is in. So what he does is first he does a measurement and finds out which side the particle is in, and then he attaches the pulley. But as soon as he makes the measurement and finds out that, okay, the particle is in the left-hand side compartment, he has to store this information. And this storage of information can be done in two ways. Either he has access to a new memory, or he has to erase the previously written memory. And this entails some amount of work, because Landau's principle tells us that the amount of work needed to erase one bit of information is exactly the amount of work which we saw being extracted from this. So basically, what is happening here is information is being converted into work, and we'll see this happening in quantum regime as well as we move along. So start with what we are going to do as use as experimental test bed is our NMR nuclear spins. So the left hand side picture that you see is an NMR tube, all right, which has a very small amount of liquid inside. And NMR qubits are nothing but ensemble of solid or liquid nuclear spins. Now, this small amount of sample that you see inside the tube has around 10 to the power 15 solute molecules. All right. Say the molecule is chloroform, which is CHCl3, and the structure is here. The carbon is at the center, and the white sphere is the hydrogen. Now, we know hydrogen nuclei is spin half from Schiff model. And not just hydrogen, other nuclei like carbon 13, 19F, phosphorus 31, all these are spin half particles. And what happens when you introduce these spin half particle in magnetic field? There's a Zeeman splitting that happens. So basically, this tube goes inside inside a superconducting magnet, which causes a Zeeman splitting. And the energy levels of these two levels are such that energy spacing between these two levels are such that you can probe this using RF frequencies. And thus you have two discrete levels, which can be your logical 0 and 1. And now you can use them as your qubits. So this is your sample NMR tube, inside which all the spins are randomly oriented, all right, at temperature T0. So you don't have a net magnetization as of yet. But then you introduce a magnetic field, and thus you get a Hamiltonian, which is a static magnetic field, and you get a quantization axis. So what happens is the entire system develops a magnetization alongside axis. Now, we can now find out what the state of the system is using Boltzmann distribution at temperature T0 using this particular Hamiltonian. And we see that we get diagonal terms, which can be thought of as populations in 0 and 1. And thus, because of the difference of the population, you get a magnetization, which we want to detect. And how do we detect it? This magnetization can be brought down. So this is happening inside the NMR. And inside NMR, you have coils, all right. And this is the NMR tube, which is inside a magnet. You had a magnetization along Z, but you gave a pulse along Y, and it came in the XY plane. Now what happens is, in the presence of this magnetic field, this magnetization starts precessing. And as it precesses, it cuts through these coils and gives us signal. We take a Fourier transform of this to get the NMR signal. And from this, we can find the expectation value of sigma X and sigma Y, which basically together gives us a quadrature detection. And from this, we can completely form our density matrix. So whichever state we prepared the system. So now you see we have a way to probe the qubit and even measure the system out. And this is just for one qubit as I shown here, but we are going to use 2 qubit system, 3 qubit system, 4 qubit system as we require. And as soon as we talk about more than 1 qubits, Hamiltonian now has interaction term inside it as well. The H0 term, as I talked about, was just a plain magnetic field on the nuclear spins, which helps us with addressability, so that we can address each one of these nucleus separately, spins separately. And the interaction, which I basically use, are of 2 types. One is just Z scalar coupling, and the other is the dipolar coupling, all right, which is orientation dependent. And we'll see, we are going to use both of these interactions. By seeing the splitting of this peak, as you see here, of the signal, we can find out what is the coupling strength. So that is going to be our experimental setup or test bed on which we are going to test various quantum thermodynamic processes and see how these quantum systems behave. So to begin with, let's start with quantum heat fluctuation relations. So second law of thermodynamics tells us that the entropy will always increase with time. But statistical mechanics also tells us that this second law is only an average law. That means it's not that the entropy always increases, but only on an average is that the entropy increases. That means there will be fluctuations. fluctuations such as times where entropy will increase and times where entropy can decrease as well. But as a whole, again, the entropy always increases. Now, these processes in which the entropy is increasing, we call as a forward process. And the process in which the entropy reduces, we call it as a backward process. So fluctuation relations are nothing but relations between the probability distribution for the forward and the backward processes. Let's see what that means. So the form of fluctuation relation will be something like this. Where the numerator is the probability for the forward process happening, that is the entropy increasing, whereas the denominator is just the opposite happening. And what this relation basically tells you is that the probability for the forward process happening is exponentially higher than the probability for the reverse to happen. That's all in this sense. All right, we are trying to see this fluctuation relation for a heat exchange between two quantum systems. So we experimentally prepare we take two qubits, prepare them at two different inverse temperatures. And by temperature, I mean spin temperature, that is the relative population of the two states they are in. And then we let them exchange heat under certain kind of flows. And finally, we see how the heat flows. So if the heat flows from hot to cold, we call that a forward process. Whereas if the heat flows from cold to hot, in which the entropy reduces, we call that a backward process. And thus the fluctuation relation for the heat exchange takes a form like this, which tells us that the probability for the heat to flow from hot to cold is exponentially higher than the probability for heat to flow from cold to hot. But minded that there is finite amount of probability for the reverse to happen. There is finite amount of probability for heat to flow from cold to hot, and the cold qubit becoming colder and the hot becoming hot. There's finite probability for this. So this is called Jarzynski-Watzke exchange fluctuation theorem, and this is valid for two assumptions. First is weak coupling strength and uncorrelated initial state. In our work, we probe all these conditions, but I won't go into the depth of it. I'll just tell you what we did. Because basically, we want to see to what extent is this relation valid, whether in weak coupling or in strong coupling, to what extent then. And also what happens if we introduce initial correlation to the system. Because initially we prepare them in a Gibbs state at particular temperature. So, the objective is to verify this particular relation. But for that, we need to find the probability distribution for the heat exchange. And experimentally, it's pretty difficult to just go for the probability distribution. So instead, we go for a characteristic function. This is the Fourier transform of it. And so the experimental setup will be take a molecule like this, all right, which has 3 fluorine nuclei, and fluorine nuclei are spin half particles. So what we will do is we'll see the heat exchange between F1 and F2. The role of F3 is just to extract the information about this characteristic function, and that we do using an interferometric technique, the circuit diagram of which is given here. So so F1 and F2 are prepared in ρ1 and ρ2, some initial temperatures, and they are allowed to exchange heat under this unit. All right. Everything else, every other gate that you see in the circuit is just to extract the information of the characteristic function, the heat exchange between F1 and F2 using F3. So finally, after this circuit, if we just see the quadrature of, we do the quadrature detection of F3, we extract the characteristic function for the heat exchange between F1 and F2. So if we do that, we get the characteristic function, which is A and B, the real and imaginary part of the characteristic function for a particular heat exchange process for a particular time. I'm not getting into those things, but you get the characteristic function and then you take a Fourier transform. And this you get a probability distribution function. So there are 3 peaks here corresponding to the peak on the right corresponds to heat flowing from hot to cold. The peak on the left corresponds to heat flowing from cold to hot. And the middle one is just no heat flowing. So, but you see there's a finite amount of probability for heat to flow from cold to hot as well. But if you take the area under this curve, you will still find the heat flowing on an average, flowing from hot to cold. All right. So that's what it means. So then what we do is we change. So this is for a particular temperature, initial temperature of F1 and F2. We change the initial temperature and see how the probability distributions vary. And we do this for quite a number of temperatures. Here you see that we have maintained them we started them both at infinite temperatures. And this you see the peak height of both the forward and backward process, same, because it's at the same temperature. So net heat. So let's not go into more deep of this, but let's talk about something which is more interesting, I think, which is introduction of quantum correlation into the system. So until now, what we have done is we have initialized the system in some kind of Gibbs state, and which is a product. But what happens if we introduce some amount of correlation into the system of form like this, and we make sure that alpha takes care of the positivity of the density matrix? If we do that, and if we introduce this particular kind of correlation into the system, what we see is that the cold is becoming colder and hot is becoming hotter. That means even now, even on average, heat is flowing in the reverse direction. All right, and we call this the reversal of arrow of time. So what we did was we took so this is the density matrix of the 2-qubit system, which are going to exchange heat. So you see the diagonal, it's all diagonal. So it's in a product state. Whereas in this exact same state, what we do is we introduce this kind of, try to introduce this kind of correlation in experiments, but there are some other components as well, as you can see. But anyways, we do this, and we see that the discord between 1 and 2 is around 0.68, which tells us that there is quantum correlations inside the system. And what we see is that when there was no correlation, heat was flowing in one particular direction. This is again the probability distribution for this kind of heat exchange. Whereas as soon as you introduce the correlation, you see the heat flow flips, and now it flows in the other direction. So this work was done in collaboration with Dr. Bijay Agarwalla, who's a faculty in IISER Pune itself, and this is published in PRI. Moving on, let's briefly talk about quantum uncertainty relations. So I won't go into much depth of this because of the time constraints. So basically what we tried to do is, we saw that previously that we tried to study the heat exchange between two quantum systems, right? But as we go to quantum levels, these heat exchange processes have fluctuations in it, all right? And people ask this question that this ratio, so we take the second cumulant of this heat exchange as the noise, whereas the main flow is the signal, which is the heat flow. So people ask this question whether the noise to signal ratio can be bounded. All right, these bounds are always biased to the field of physics, and people came up with bounds. What this means is that no matter how precisely you measure a heat exchange process, there will always be fluctuations in the system which can be bounded as such. And people gave certain bounds. Some of them are your very tight bounds. Some of them were loose bounds. And we, for the first time, did a experimental study of these thermodynamic uncertainty relations, and to what extent are they valid. We try to see under different coupling strengths. We try to see under different coupling strength, time of evolution, how these bounds behave. Where epsilon is the entropy produced in the heat exchange process. So I show here results for 2 parameter regimes, and you can see this blue line is basically the first relation. So sigma, this entropy can be broken down into delta beta q, which is the signal, and what you get is basically this. If this relation dips below 0, that means this bound is getting violated. For a certain kind of parameter, it did not. For another kind of parameter regime, it did violate, and it came below 0. So this was the first experimental study of the thermodynamic uncertainty relations. Let's not go into much depth of this, but this was again done in collaboration with Dr. Bijay Agarwalla and Devira Sigal from Toronto University. And this was in PRR and rapid communication as well. Moving on, coming to an interesting topic on which I think today there's a keynote talk as well, which is time crystals, although this is not a quantum time crystal. So time crystal, let's see what that is. So space has this translational symmetry. So basically what that means is you do something here or 2 kilometers away, if the space is homogeneous, things are not going to change. But crystal breaks this symmetry and gets a repetitive pattern, all right. Now time also has this same translational symmetry. You do something today, you do something 2 hours later. It's going to be the same. Now, the question was asked whether there are systems which breaks the symmetry of time spontaneously. All right, and Frank Wilczek coined the term time crystal. The systems which spontaneously breaks the symmetry of time. and later and it was found that the time crystals, the property of time crystal can be displayed by these driven quantum systems. So what I mean by that is, suppose you have a Hamiltonian which is basically flip and delay, flip and delay. So flips are basic. Yeah.
So 5 minutes are left.
Okay. So okay. So so you have flips and you have delay. You have. Are you sure 5 minutes are left? I started around 45, right?
Yes, there are some questions. So 25 minutes are for the talk and 5 minutes for discussion. And there are some questions I can see in the chat box. So
I see. I see.
it would be better if you finish.
I see. Okay.
Okay.
Okay. So the Hamiltonian is basically spin flips and delays. So you see this Hamiltonian has a period of t, whereas the nuclear spins are flipping with a period of 2t. Right. So what you see here is that the system itself is breaking the underlying symmetry of the Hamiltonian. All right. Now, is it the only criteria required for a time crystalline behavior? No. The thing is that if you introduce error in these Hamiltonian, the system should still lock onto its 2t period. All right. So that's a requirement. And later on, you will see, although I won't discuss it, but this time crystalline behavior comes around because of disorder and interaction in the system. We experimentally see this for a star-shaped cluster, in which we have a central spin coupled to a lot of satellite spins all around, as we'll see in experiments as well. And they are coupled using just ZZ coupling. And we start with an initial Z magnetization. That is what we are going to observe, the net magnetization. And what we do is we subject them to this kind of a pulse sequence, which is delay, and then a pi pulse, delay, and pi pulse. And we are going to introduce error in these pi pulses to see how the Z magnetization reacts. So basically what I mean is, suppose you give a perfect pi pulse, all right, and you see the net magnetization, and you start with the Z magnetization and you keep flipping it. So it keeps flipping. And if you see the Z magnetization, you get an oscillation like this. And you see the decay here because of the T1 relaxation. But now if you introduce some amount of error into the system, what happens is this magnetization now no longer comes directly below, all right? And there are, and the error adds up. And now if you see the Z magnetization, you get a beat formation, something like this. So now we call this a time crystal. So it's quite interesting to note that both these systems have same amount of error in them, all right? But one has time crystalline behavior, the other doesn't, all right? So one is robust against any error in the pulses, other is not, because of the presence of interaction, as we will see. So I had an explanation, semi-classical explanation about why this is happening, but in interest of time, let's skip it. We also see how this time crystalline behavior becomes better as the number of satellite spins increases. This is just computation. So the experiments are done for three kinds of nuclei, which is with a varying number of satellite spins. So the first nuclei compound, as you see, has carbon-13 at the center, which is spin half particle, and hydrogen surrounding it, 3. Similarly, here you have phosphorus surrounded by 9 hydrogens, and here silicon surrounded by 36 hydrogens. So and all what we do is we take the satellite spin, take the central spin, we give a delay, and we give error some pi pulses, and we repeat this and try to see how the Z magnetization behaves. So now this particular molecule gives us a very nice experimental frontier, because the carbon has 2 isotopes, so carbon-12 and carbon-13. Carbon-12 is NMR inactive, that is it's spin 0, whereas carbon-13 is spin half. So basically here there is no interaction present, whereas there is interaction here. And if we introduce the same pulse sequence with varying amount of errors, these errors are in radians, you see in one case it just decays away because of these beat kind of oscillations. But here this maintains its oscillation frequency. And we take the Fourier transform just to illustrate on this. We see here that we start seeing subharmonic peaks. But here it tries to maintain its peak even till 30% error in pi pulse, which I think is pretty remarkable and can be used in various quantum controls and in systems which do not have very good control. So same thing we do for other compounds as well, for different number of satellite spins. And we see this. This was done in collaboration with Dr. G.J. Shrijit. This was also accepted as an editor suggestion and featured in physics. I guess I don't have time, do I, anymore? Hello?
Yeah, you have some time, 4 minutes maybe.
But just before that, you said 4 minutes.
Okay, you take 2-3 minutes. Okay.
I see. I see. Okay, so the same thing now we would like to do for solid state systems. So the time crystal that you just saw was liquid. All right, and in liquid we had an interaction something like this. But now as soon as we come into solids, we have another kind of interaction which I just talked about, which was a dipolar interaction. So now this dipolar interaction is directional. So it depends upon the vector joining the two qubits, spins, as well as a net magnetic field that is applied. And because of this, the strength of these dipolar interaction has a theta term inside, which is the angle between the vector joining these qubits and the magnetic field applied. Now you can guess there can be a particular angle of theta for which this disappears. And this turns out to be 54.74 degrees. And so what happens is if you take your sample, if you spin it very rapidly, what happens is all the anisotropic interactions go away. And if you align that spinning sample at 54.74, the dipolar interaction goes. So now we have a technique through which we can slowly remove the interactions away and see the time crystalline behavior coming into picture and then going away. So we do the same thing for a molecule like this, in which the green spheres are your hydrogen and the red ones are carbon 13. And we again want to see the Z magnetization, and we are going to introduce error in it. And you see, this is the oscillation using with dipolar coupling in it. All right, and we introduce an error of 20% in it. And you see, it's very hard to distinguish between which has error and which doesn't. That's the strength of time crystal. And then what we did was we scanned over the time of this delay, and we saw that the most optimal one was 1 millisecond. So we chose that. And what we did next was to see whether interaction plays a role or not. We decoupled the satellite spins and tried to see what happens. So you see the blue line is 20% error without decoupling the interaction, whereas the green line is the same amount of error but with decoupling. So you see it just goes. Next, what we did was the spinning business, as I told you, because we have now control over how the interactions, we can slowly remove the interaction from the system by spinning the sample. So you see this is without spinning, whereas this is with 2K spinning, and slowly we increase, and we see by 8K spinning, the one with the error, which is the blue line, completely disappears. We also take a Fourier transform of it to just see this thing. So you see this line corresponds to 2K. You can still see the central peak. But as soon as you go to 8K, which is here, you start seeing the subharmonic peaks coming up. So that's the solid part of it, of the time crystalline behavior. There's one more, but let's not go there. Let's stop it here. They together, I think, form what I would like to think of as a quantum technology, because fluctuation relation helps you to understand how heat flows inside a quantum thermal device. TUR lets you know the fluctuations that are going inside it. Time crystalline behavior helps you probe these systems even if you do not have good control over your system. But if there are error in the control, it's even then you are able to efficiently manipulate or evolve the system. The last thing I did not talk about because of the interest of time, but together they form quantum technology, I would like to believe. So that's my institute, ISA Pune, where I'm from. I'm in my last year of PhD. That's the okay. 3 pictures are not coming, but these are my collaborators, my guide, Professor T.S. Mahesh, and all these collaborators and their other collaborators. Yeah, thank you. And that's the NMR Center.
Thanks, Soham, for the nice talk. And there is a question from Professor Aditi Shende.
I see.
Hello?
Yes, ma'am. So this chat box is not visible right now. So,
no, I can
ask the question.
No, okay. I can see the chat box.
Okay, so you can.
Yeah, I can ask the question to stupid. I mean to. So I have first I have a stupid question. So you said that you can in the first part that you can go. You have tasted when you have infinite beta. That means zero temperature. That I understand. Yes. So how will you manage this?
Just a second. Can you see the screen right now?
No, I cannot.
No.
Just a second. Is this visible now?
Yes, yes,
Okay,
yes.
just a second. Let me get back to the slide. I think it's in fluctuation relations, right?
Yeah, exactly. So
Okay,
you
okay.
said that
Just a
there is,
second. So here, you mean, right?
yeah, you said that beta infinity, right? So what I
Yeah,
understand is
yeah.
zero. Yeah.
So no, this beta is not, you see there's an inverse here. All right. So beta 2 inverse. So basically this means infinite temperature, but I get your question. So the above line reads that beta 1 inverse is 0, which basically means temperature is 0. So what do you mean by this is basically, as I said, that I don't mean actual temperature, I mean spin temperature. And by spin temperature, I mean the relative population of the spins in the two levels. So when I say 0 temperature, what I mean is a pure state.
Okay. And then I have just one question that in this part, you said that your initial state you have changed to the, initially you have two thermal states, then you actually introduce a discord,
Yes,
right?
ma'am. Yes, ma'am.
And so my question is, if you, and you show something, so does the result remain same if you introduce entanglement instead of quantum discord?
So that's what it depends a lot on. So right now what you saw was on an average heat was flowing from cold to hot, and thus you see kind of a refrigeration happening, right?
Yeah.
But if I introduce some other kind of correlation, it's only because I introduce such a kind of correlation that this happens. If I introduce certain different kind of correlation, what you might see is the flow of heat from hot to cold becomes faster. All right. So there will be no refrigeration, but the heat flow will become faster. So it depends upon what kind of correlation are you putting into the system. So it's not that you put in correlation and it will always cause a reversal of arrow of time. Only certain form of that correlation will cause that. If you have certain other kind of correlations, it might speed up the heat exchange as well between hot and cold. Does that answer the question?
So Swati, can you read?
Yes, ma'am. No, I can read. So there is another question from Sheila Dittimal, that is there any quantitative relation between the correlation strength and rate of heat flow from colder to hotter?
So that's what, as I said, I think this connects to the previous question that was asked by Aditi ma'am, that this form of correlation depends a lot. So just if you have a form of correlation which does not causes reversal of arrow of time, all right, no matter how strong the correlation is, it will not cause that. Just because I have a form of of correlation like 0, 1, 1, 0 and 1, 0, 0, 1, I am seeing this. If I change this correlation to something else, I'll see something else. Maybe the heat flows from hot to cold even faster, all right, or no change at all. Although that's very difficult, but this form we are seeing because of this particular form of this. And of course, if you increase the strength of the correlation for this particular form, then you might see the heat exchange becoming faster in the reverse as well. Yeah, sure. So if I increase the discord, I would see the reverse heat flow becoming even faster. But I don't think whether there is a parameter which I can rely upon and say that changing the correlation strength to some particular amount will give me heat exchange to this much amount. I don't think that exists, but one can of course look into it. Does that answer the question?
Yes. Thank you.
Thank you.
Okay. Is there any other question?
I can see a few. What quantity you measure in the experiment?
So there is a question from Utkarsh, I think, that what quantity you measured in the experiment and how to get m naught as a function of time.
I see. So what we measure, so as I showed in the initial slides, so here, as I showed you, what we do is we basically take a quadrature detection. So what we measure is the expectation value of sigma x and sigma y. And once we have that, from that we can reconstruct the entire density matrix. Once we have a density matrix, we can do whatever we want, if we have the state of the system. So our measurement is always in experiments, the magnetization, and thus the expectation value of sigma x and sigma y. And from there, we can find the populations of the state and whatnot, and thus the magnetization as n naught, as you mentioned. It's fine. Yes.
Okay. There is another question from Kapil Sharma that what do you think that NMR techniques is far better than superconducting one in the context of developing quantum processors?
Yeah, I
In
mean, this is very well known that NMR will never be tabletop quantum computer or quantum device, because we all know, because of the weak signals and other problems. That's scalability is not that big an issue, but of course superconducting qubits are much better to realize actual devices. But see, what we are trying to do here is not develop devices. We are just trying to test physical like basic physics stuff. So I think NMR itself provides a very nice place to act as a test bed for these quantum simulations. Yeah, but of course, superconducting qubit is one of the techniques which will pave the way for quantum technology. Yes. Does that answer? General NMR is very noisy qubit. Yeah, it is pretty noisy. Yeah, signal is pretty weak. Yeah. But again, we do an ensemble, our measurement is based on ensemble averaging. So we can get to some extent signal, but it's noisy. Yeah.
Okay. Thank you, Soham, for this nice talk.
Thank you so much. Thank you for organizing this. This is, I know this must be such a pain for you people as well, but appreciate it. Thank you.
Okay, thank you. Now we.
Yeah. Okay. Thank you, Swati, and thank you all the speakers in this first half of the morning session.
Thank you.
Yeah. So and now we move to the next part of the morning session. So this session will be chaired by Shomo Kanti Bosch. I think Shomo is online.
Yeah, I'm online.
Seoul National University. So he recently moved to Seoul, and I'm really happy that he came for a testing as well as chairing the sessions and giving a talk even when he is quarantined. So thank you, and now you should chair this session.
Okay. Just a moment. Okay. Are the people online? Arun Sherawat and Ananda Maiti is there. Yes, Arun is also here.
Yes, yes.
Hi, Arun.
Hello.
After a long time, we are talking.
Yes.
So today in this session, the first talk is by Arun Sherawat. He is in HRI. He is a postdoc there. And he will be talking about allowed region and uncertainty relations for angular momentum observables.
Yes.
I hope I'm a bit interested in the topic, so I hope it will be a nice talk. Now the stage is yours. You can continue.
So let me share the screen.
Arun, can you increase your voice a little bit?
Yes.
Okay.
So is it audible now?
Yeah, now it's audible.
Okay, and let me also on the camera, I guess. Just a second.
আপনার ইনভেন ডিস্ট্রিবিউটর হলো বাসাই ইনভেন গ্রামের বিভাগ নিশ্চিত করতে এক অনুগ্রহ করে আপনার কনজিউমার নম্বরটি
and then I open my camera and I share the screen. So
আপনি যে কনজিউমার নম্বরটি অন্তর্ভুক্ত
It's probably online from mobile, and the voices from the mobile is coming. Right?
Sorry. So the screen is visible, I guess.
Make it full screen, Arun.
Yes, because I was.
If you cannot, then just.
No, this one is.
Yeah.
Okay, so. I don't know. Okay. So
from the left hand side, you cross it.
Yes, but like my cursor goes, and then there is this
Yeah, I
fine.
think yesterday also there was a problem of
Because
Sharon.
cursor, yes.
So maybe you just start with this is fine. I mean, we can.
Arun,
Okay.
Arun, you do one thing. There is a cross sign, right?
Uh-huh.
In the above. Just
Yeah.
before, just beside that, there is a box, right?
Yes, yes, I know. But I
No, no,
cannot click
no, no,
because
no,
there
no,
is a
no.
something here.
I mean, just beside the cross, there is a
Uh-huh.
box, right?
So I can open this one,
No,
but when I
not
go
this
down,
box. Not this box. There is
okay,
a cross sign. Just beside that, there is a box.
this box.
No,
Oh,
Just
this box.
that one, that
Okay,
one.
okay,
Now
okay.
you can access.
Yes. So yes,
oh,
thank you.
So yesterday I have invented this process actually.
Okay. Uh,
great. So,
because this okay. So I can start now.
Yeah, sure.
Okay, so thank you very much to all my co-organizers for their hard work and all the three faculty members for their supervision and support. Without their determination, this conference wouldn't be possible. And thank you so much for giving me this opportunity to present a talk. And this talk is based upon this paper where I will present some result of this paper. So I start. So the outline is I will tell first what is the allowed region and for expectation values. So you can think
Problem with the HRI interview.
will show how it is related to quantum to classical transition. I will also show that how allowed region is related to quantum phase transitions. So I start. So we can start with the question that can real number x be the expectation value of an observable capital X? You can say the answer is yes if and only if x lies between its minimum, which I denote by small m, and the maximum eigenvalue. So for example, if you have n spin half particle and you are measuring its magnetization, then you will always find a value between minus n half when all the spins are down and plus n half when all the spins are up in the direction of x. So you can ask similar question by taking two real numbers. Can these two real number x and y represented by this purple pink point here be the expectation value of two operator x and y? Here the expectation value is taken from the same state row. So you can give an answer something like that expectation that x must lies between extreme eigenvalue of operator x, and similarly y must lies between extreme eigenvalue of y, which means that this point must lies in this box, right? So here I take x and y 3.2 3.2, and the two operators I am taking here is a square of angular momentum operator jx and jy, and j I am taking 2. So we know that angular momentum operator can jx can take eigenvalue from minus j to plus j. So the maximum eigenvalue will be 4, and since this is an integer, j is a integer, so the minimum eigenvalue of jx square will be 0. So there is a two parallel line on 0 and 1 which are, and two parallel line in this direction. So this is the box which I call h. You can, so if the point does not lie in this square, then or rectangle you can say, then they cannot be the expectation value. But here this point lies here, and we will see that this is a necessary condition, but this is not sufficient because there is a constraint on the expectation value in each direction. So I take two directions. Okay, let's talk about this direction. So suppose this arrow makes angle phi with the x-axis, where I'm plotting expectation value of operator x. So then this is the unit vector. By taking dot product with x, by taking dot product, I get an operator lambda. which is a function of parameter phi. And expectation value of lambda can be written like this, as a linear combination of x and y. And just like expectation value of x must be less than x maximum, then expectation value of x lambda, expectation value of lambda must be less than its maximum eigenvalue lambda m, which is a function of the parameter. So what this, you can see there is a constraint on expectation value of x and y for each phi. What this constraint means is that there, for each direction, there is a hyperplane which divide the whole two-dimensional space, because I'm taking two operators here, x and y, two-dimensional real space, they are Hermitian, so this is real space, into two parts. The part which is in the direction of arrow is called outside, and the part which is opposite to the arrow is called inside. So the point must be inside for each plane. So you can see for this plane, the point is inside, but for that plane, the point is outside. Cannot be the expectation value of jx square, jy square when j is equal to 2, right? So if you draw such planes for all angle phi, you will get picture like this. So these are for all different phi's. So the region bounded by these planes is called allowed region. So if you take Pauli operator, you will get a block sphere in this way. Okay. So, and you can see this point is outside, even though this is in the square, which is this, you can see there is a square. So this is not the, they cannot be the expectation values. So, so who give us the eigenvalue? Maximum eigenvalue is the maximum eigencat. So suppose phi cat is our maximum eigenvalue cat. So if I take my state in this maximum eigenvalue cat and I compute the expectation value, then I will get an equality sign here, which means that the maximum eigenvalue state saturates this inequality, right? So which means that the boundary of this allowed region come from this maximum eigenvalue states. So if I find out all those maximum eigenvalue states for all those angles, and then this will give me the parametric form of the boundary of the allowed region. Whatever is inside is allowed, whatever outside is not allowed, right? So this kind of thing you can find, I mean, like in a book, which is one of the book is like numerical range, and or these things are also called field value of linear operator and matrices, right? So I want to make one important point here is, so when I multiply minus sign on the both side, I take minus lambda, then this inequality flips, right? And I can multiply minus one side on the both side. So which means that the minus lambda is the lowest eigenvalue of minus lambda operator. So if minus lambda operator is Hamiltonian in some system, then the minus lambda m is my ground state, and then this phi cat are my ground state cats, right? So you can see because I'm changing the parameter of the Hamiltonian, so this phi will be the parameter of the Hamiltonian. So I'm changing the ground state. So all the information about the ground state is encoded in the boundary. So by looking at the boundary, you can see how the ground state is changing, right? If you see there is some sharp change in the boundary, that is a signature of quantum phase transition, because there is some drastic change in the ground state of the Hamiltonian. Okay, so this is how you can, by looking at the boundary, you can study the quantum phase transition. You can detect it. So now I don't go in this direction. I go that how to define uncertainty functions. That is our contribution on this numerical range. Generally, two expectation value are needed to define an uncertainty function, uncertainty measure. Like for example, expectation of x and x square. So you have a standard deviation. So question what we are asking is, suppose we have only one expectation value, operator x, right? So how to measure uncertainty then? So when only the expectation value, only the mean value of x is given, how to measure uncertainty? So we know for sure, I mean, as I told you, that this expectation value of operator x lies between its extreme eigenvalue, and we can only be certain in these two cases. For example, if we get expectation value is x minimum, then we know for sure that the system is in minimum eigenstate of x. Or if we perform measurement, we always get xm outcome, right? So we want our function which give zero value at these two extreme point of the interval. So here I am defining uncertainty function for single observables. Now the second requirement is mixing states increase uncertainty. For example, if we prepare 100 spin half particle polarized in x direction, and then another 100 half particle polarized in y direction, and then mix them, the total state of 200 particle will be a mixed state, and this will have more uncertainty. So we want concave function, which concave function usually increase under mixing, which is concave combination, mathematically speaking. So to define such a function, we take we take this p, which is a function of expectation value of x only. So p is a probability, because when x is x minimum, then numerator becomes 0, so p is 0. When x is x maximum, then numerator denominator cancel each other and p is 1. So as x goes from minimum to its maximum eigenvalue, I mean expectation value of x, then p goes from 0 to 1. And then this probability you put in this formula, which is Shannon entropy, and then you get your concave function. You can also get convex function, but because minus of concave function is a convex, so you can also use convex function. So we call it a certainty measure, but they are basically same. You multiply minus sign and then you flip one to other. Okay, so one more main important difference what I want to make is, this is not the conventional Shannon entropy where these probabilities come from projectors, because this probability comes from a positive operator, not from projectors, right? Rank 1 projector. And the important point here is this usual Shannon entropy become 0 when a system is in any eigenstate of operator x. But here this h becomes 0 only when x is in extreme eigenstates, right? So that's why you will get those uncertain, I mean, these uncertainty relation based upon this h will be qualitatively different than those based upon conventional entropy uncertainty. So I move next. So how about two observables, because we need at least two to have uncertainty relation. So we know that sum of two concave function is a concave function. So just like x, we define hy, h as a function of y for observable y, and take sum of them. And this combined function is a combined uncertainty measure for observable x and y, and this is defined on this. You can see there is a square here, 0 to 4, 0 to 4 there is a square, and then inside square you have allowed region, which is the green part is interior and the red is the boundary, and this is elliptical region, and this top one envelope is this combined function. But we are interested only on the part which is on the allowed region, so only this dark orange part. So this x belongs to E, allowed region, which belongs to this cube or square in this case. Okay, so concave function, and this is a convex set. A concave function on a convex set reaches its absolute minimum, because we have to find the lower bound h, which is global minimum, so that we can have uncertainty relation. So concave function on a convex set reaches its minimum at the boundary. Okay, and we know that boundary is parameterized by this extreme eigenvalue states. So if we take these two and put it here, then we get this combined function as a function of a parameter phi. So this I'm plotting here as a parameter phi. That means like I'm moving on the boundary up and down, and it reaches its minimum, absolute minimum, which is 1/2 in this case, at these two values, right? So this 1/2, so this lower bound will be 1/2. This will give me uncertainty relation, and I also get where it reaches its lower value. So the corresponding phi will give me phi cat, which will be the minimum uncertainty cat, right? So so minimum uncertainty cat always in this case will be some ground state of some Hamiltonian. Okay. Now one more important point is you can see this minima, this function reaches minima which is close to the corner. Okay, so suppose this point, this corner belongs to the allowed region, then the minimum will be 0. So we get null uncertainty relation, means like the lower bound is 0 only when, if and only if a corner of the rectangle belongs to allowed region. And this happens when there exists a common eigencat that correspond to extreme eigenvalue of x and y. So it must be extreme eigenvalue state common for x and y, otherwise you will, because conventional uncertainty relation become null when the x and y share any eigenstate, but in this they become null only when they have extreme eigenvalue state. Okay, so this is also another difference in comparison to conventional uncertainty relation. Now I will show you some examples. In the case of examples, I take angular momentum operator. I don't know. Can you see this part? The top one part. Okay, but they are angular momentum squares, jx square and jy square, and this is for angular momentum quantum number j1/2, spin 1/2, spin 1, spin 3/2, spin 2, spin 5/2, spin 3, and spin 4, and when j is infinity, this one. Okay,
Arun.
Yes.
You need to hurry up. You have about 5 minutes.
Okay. Okay, but I started, I think 11:15 something, or 11:14 something.
Yeah.
Because it was little late. I can
Okay.
hurry up. I mean, like I can
No,
finish in 10
I mean,
minutes.
I'm just telling you.
Yeah, sure. So let me tell you a bit more things about these.
Okay. Okay.
So here, in case of spin half, both these angular square of this angular momentum, they are proportional to identity. So you only get a single point. In case of spin 1, they commute. So you get a polytope kind of structure, and then you get an ellipse, and then spin 2, you also get ellipse. You have seen for j is equal to this one, right, on the first slide or initial slides. And then when you go beyond 2, then this allowed region starts changing its shape. It's become more and more and more like a triangle, and it actually becomes triangle when j tends to infinity. Now when we define this uncertainty function, combined one on this region, so let's start from here. So you can see this is a square, so it take this joint combined uncertainty function takes its maximum value, which is near the corner, and these corners are getting closer and closer to the squares. So that's why this h is monotonically decreasing, and it goes to 0 because these corners are part of the allowed region. So our uncertainty function become null when j goes to 0, because when j goes to 0, then there exists a eigenstate, there exists a cat which is a common eigenstate of these two operators. And when you take a square, this become extreme eigenvalue state, because it's a j square, one square will be there and 0 will be there, and I divided by j because otherwise you will get infinity everywhere when you take j tends to infinity limit. Okay, so this is, that's why this become 0. And there is one more point I want to make here. In case of j is equal to 2, they share three common eigensets corresponding to these 3 points, these two operator. But if you take conventional uncertainty relation, that will become 0, but in our case we get a 1/2. So you see that our one don't become 0, it only becomes 0 when the common eigenstate is extreme eigenvalue state for both the operators. So what we learn here, that if our uncertainty relation work when the standard uncertainty fails to capture the incompatibility of observables, because if two operators share one common eigencat, the standard uncertainty relation become null. I mean, they become trivial, but our don't. And then second one thing is we have seen that quantum to classical transition, because these two operators, they don't commute when j is finite, but when j is infinite, they start commuting. So you can see that this allowed region become a polytope, which is a signature of classicality. And the second thing is, you see that our uncertainty relation become null when j tends to infinity. So you can see that as j increases, these operator become more and more classical. Okay, and they so these are allowed region for these anti-commutators. And similarly, I plot here uncertainty bound, and this is for j cube I plot. So as this is j is equal to 1, spin 1 is j cube, this I take 3 operators, it is a sphere, then sphere start contracting, and at the infinity, in fact it is 10, j is equal to 10, it become octahedron, and in fact it become truly octahedron when j tends to infinity. And here I plot this the maximum eigenvalue state lambda, like we have lambda operator, and then it's a highest eigenvalue is lambda maximum I plot here, and second largest. And you can see, you can think the top one is a ground state. If I multiply minus sign, then this picture flips. So top one is a ground state and lower one is a first excited state. So the gap between them closes as j tends to infinity, which is also a signature of phase transition. So this I mean, you can see there's just some sharp change at the ground state energy, and also you can see on the boundary, because it was smooth and then the boundary have some sharp edges and faces. So this is signature of quantum phase transition. So these two things I tell you, but I can stop here just by saying something. This is for J4, and you can use quantum definity theorem to get the uncertainty, to get these allowed region when j tends to infinity analytically, which I mean, I can explain if I have some time. I can basically make these 3 points what I want to say. So consider spin j system as a composition of n spin half particle. Then you restrict your total angular momentum operator on the symmetric subspace of symmetric subspace of n qubit Hilbert space. Then you get jx jy, and then you apply the quantum definity theorem, which is a third statement, which says that all the extreme point of this symmetric subspace come from the single qubit pure states. Okay, and the single qubit pure states are Bloch sphere. So x, y, z has to follow this condition. And to get the allowed region for jx square or j power gamma, you have to apply this transformation. So apply this transformation on a sphere. So if gamma is 1, sphere stays sphere, nothing is identity. When gamma is 2, sphere become plane. When gamma is 3, then sphere becomes this, and gamma is equal to 4, sphere becomes that. And when you apply, and then you have to take a convex hull, because this is the extreme point. To get the full region, you have to take convex hull of this, which basically means you have to like attach, draw lines between these, and you will get something like this. So convex hull of sphere is sphere, convex hull of triangle is a triangle. You see, and convex hull of this one is a octahedron, which we got, and convex hull of this is that object. So here I stop, and you can similarly do for anti-commutator. So the conclusion, I just come to the conclusion. So I have shown you that how to get allowed region in general, and particularly for power of the angular momentum operator, and for their anti-commutator, for J, spin half, 1, and up to infinity. And I showed you how to build uncertainty relation on the allowed region, and how you can see the quantum to classical transition of certain operators. And I have also shown how it is connected to quantum phase transition. But before I end, I just want to say that where it all begins. So this is the slide. So this is like the top one is uncertainty relation for these the standard one, like a Robertson uncertainty, or some people call it Heisenberg uncertainty relation for Pauli operators, right? And then this is the condition of positivity, which defined allowed region. Okay, so if you plot this, if you bound the region based upon the top inequality, which is uncertainty relation, you get a is uncertainty relation, but they are not allowed because they don't satisfy this one, which means that uncertainty relations are necessary conditions on the expectation value, but they are not sufficient. Okay, so this was the beginning of this whole story. Okay, that's all. Thank you.
Okay, Arun, nice talk. Now we have a question from Professor Sen. Why is it that the classical case is a polytope while the quantum case is not? Hello?
Yes, yes. But I think is in this case, it turned out to be polytope. It is generally not, because you see, in case of anti-commutators, when J tends to infinity, you have still some smooth curvy part. It is not polytope. In this case, it turned out to be polytope. And also this uncertainty relation also don't become trivial in this case. So J tends to infinity, not every operator goes to commute, not every operator become classical. So it is these operator become classical plus their square become classical, also their cube. So you can see when you take anti-commutator, you don't get you get some curvy part also.
Okay, so I have a small question.
Yeah.
So when you say this operator at the infinite limit, it goes to classical, and some of them don't go to classical.
Yes.
So my question is that, can we, I mean, this is calculation we can do and see whether it is going to classical. But is there any physical context based on which we can say, okay, this is going to be classical, this is not going to be classical, no matter what you do?
I mean, so this one we can see. I mean, like I mean, I don't really understand. Can you please make it a bit more clear? Okay. I mean, like
okay, let me give you an example. For example, the Bode's correspondence principle, we go for the high end case. Then the average behavior is so dominating that you can say, okay, state is more or less classical. in a quote unquote classical sense.
Uh-huh.
So from that perspective, can you say that some average behavior is so dominant that we no longer have some quantum effect?
Yes, because like there's a Holstein-Permakov transformation where you can expand these operators, right?
Okay.
Where which have first term, first order, zero order, like it's like a Taylor series, right?
Yeah.
So you can do that, and the first order is a commuting part, and then it have some non-commuting part. But when you take those j tends to infinity limit, so only the first zeroth order survive, all become zero, all other higher component become zero, so only commuting part survive.
Okay.
Right. So in this case, I mean, in some other operator case that like when you take the limit, still non-commuting part left, then it's so in this case, like only commuting part, because their non-commuting part goes to 0 1 over j, order of 1 over j. So when you take j tends to infinity, that non-commuting part order is goes to 0.
Okay. Okay, looks like there is no other question.
Okay.
So let's thank Arun for his nice talk.
Thank you so much.
And the next speaker is Anando Gopal Maiti. Is he online?
Yes. Am I audible?
Yeah, you are audible. So let me check your screen.
Am I visible?
Let me see. You are visible. Okay.
Let me share the screen.
Okay, are you ready?
Should I start?
Wait.
Yes.
Okay, welcome to the second talk of this session. It's by Ananda Gopal Maiti. He is currently a PhD student in SN Bose National Center for Basic Sciences, Kolkata. And he will be talking on detecting non-Markovianity via uncertainty relations. So now, Anando, the stage is yours. You can start.
Thank you. Thank you, Somoda, for introducing. And I would like to first thank the organizers for giving me the opportunity to present our recent works on detecting non-Markovianity via uncertainty relations. This work has been done jointly with Dr. Samode Bhattacharya, who is an assistant professor at IIIT Hyderabad now, and Professor Archana Majumdar, who is my mentor at SN Bose Center. So first, I would like to say that my internet connection is not very strong. So if I can stop my video, then it would be better for streaming, because I am now in a remote place. So
yeah, sure. You should stop the video. That will help you.
Oh, okay. Thank you. So the outline of my talk is like that. First, I will try to motivate what the work is, and then I will introduce some basic notations and definitions regarding this work, and then I will go to the main results, which includes the violation of uncertain relations and how it is useful to detect non-Markovianity, and then I will show some examples in favor of this, and then I will show that variance can be used as a witness of non-Markovianity, and then I will go to a special dynamics as unital dynamics, and based on this, the non-Markovianity can be quantified, and I will conclude finally. So the motivation is like that. In recent years, it has been realized that non-Markovianity can act as a resource in various information processing tasks, like perfect teleportation with mixed states, efficient entanglement distribution, so improvement of the capacity of a quantum channel, also efficient work extraction. So, but for this case, it has been shown that the information backflow from environment to the systems works as a resource. But in order to use that resource, first we need to detect the signature of the resource. So for the case of very large stationary environment, Born-Markov approximation leads to the CP divisibility of the dynamics. I will explain what is CP divisibility in the next slide. However, in realistic scenario, when the system and environment coupling is not sufficiently weak, Born-Markov approximation is not valid. And as a consequence, the CP divisibility may break down, which lead to the observation of the information backflow. Now, when there is an information backflow from the environment to the system, that is, whenever there is divisibility breaking, the choice states are not anymore physical states, and they contain at least one negative eigenvalue. But on the other hand, positive definiteness of a state is necessary for uncertainty relation to hold. So this violation of uncertainty relation thus can be used to witness non-Markovian dynamics. There are many definitions of non-Markovianity, but we will start to the property of divisibility as a definition of quantum Markovian process. So see that system and an ancilla sharing a maximally entangled states, and system is surrounded by its environment and interacts with the environment. Then the various irreversible phenomena like decoherence, dissipation, etc. takes place. So that the theory suggests that under the result of decoherence, while interacting with the environment, the system loses its information and monotonically goes to the steady state. This one-way information flow characteristics by the monotonic relaxation towards the stationary state. That means from the system to the environment, this one-way information traffic is a direct consequence of Born-Markov approximation. Now, what is Born-Markov approximation? That the environment is approximately it is like that the environment is too large that it is almost unaffected by the system, and the environment has no memory of the past. So now what let me first define some basic definitions. So a map lambda which takes a system state rho s from time t equals to 0 to some later time t, it's a dynamical maps. It preserves hermeticity and trace of the operators. Means if you apply trace on this trace of rho s0 is equals to trace of lambda rho s0. It is a positive maps. What does it mean? That it maps a positive operator to a positive operator. That is a valid physical state to a valid physical state. And mathematically, this map from some bounded Hilbert space to another bounded Hilbert space, it's said to be positive. That is, when it takes all positive elements to a positive elements. This lambda rho greater than equals to 0 for all such rho greater than 0. And it is called k positive if for any complex k-dimensional complex vector space, you just increase the identity tensor lambda this map is greater than 0, then it can be called as the k positive. Now when it is called completely positive, for all such k belongs to this natural number, if the extension of the map with identity is greater than 0, then it is called completely positive. Now the divisibility is defined in this way, that suppose the map lambda from time t equals to 0 to some later time can be written in this form, that is first the map is acting from 0 to s and then s to t, where s is some intermediate time. So this is called p divisible if this map, this lambda ts is positive, and it is called cp divisible if it is completely positive for all such time interval 0 to t. And how to check whether the map is CP or not? Take its time evolution. This map lambda is taking the state rho from time t to t plus epsilon, and find its corresponding choice states. What is choice state? There is some famous Choi-Jamoy-Lukowski isomorphism that for corresponding to any map, you can find its one-to-one correspondence to a state. So how to find the state? You act lambda on one side and this map on other side, sorry, identity on one side and this map on other side over a maximally entangled state. And for complete positive CCP complete positivity, you just need to show that this is always greater than 0 for all the interval. So, however, in our work, we will start to the Lindblad type generators and Lindblad master equation. Uh, 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 in a famous result by Gorini, Kosakowski, Sudarshan, and Lindblad, says that this is a dynamical map. D rho by dt equals to L rho. That is the Lindbladian, and this Lindblad form of master equation has first as unitary part, and the latter one is some dissipation and decoherence type term are there, and this lambda k are called the Lindblad coefficient. And this Gorini, Kosakowski, Sudarshan, Lindblad theorem says that a necessary and sufficient condition for complete positivity of the dynamics is that all these decay rate gamma k's are greater than 0. Then we can say that this is completely positive. However, there are emergence of the concept of not completely positive. And this was first appeared by Pechugas in 1994, and then by Sudarshan and its co-workers. That is when the initial system environment state is correlated. That is when it is not of the form this rho s tensor rho e, the resultant dynamical map will not a completely positive map. That means it has at least one negative eigenvalue. Suppose a map lambda from 0 to t, which can be written in that form for some intermediate time s. You see that this from time t equals to 0 to t, the map is always completely positive. And also from S0, this is completely positive. But complete positivity may break down into intermediate dynamics. Because in that form, the system and environment cannot be written in that form. When it's actually written in that form, it cannot be written in rho s tensor rho e form. So the complete positivity may break down into intermediate dynamics. So there are various measures of the non-Markovianity. One of them is RHP measure. That is when this non-Markovian behavior is attributed to the deviation from divisibility, and quantification of non-Markovianity is done based on the amount of deviation. How? You take this choice Jamailokowski isomorphism, that is epsilon tensor 1 over a maximally entangled state is greater than 0, then it is completely positive. Now you define a quantity f, which is a trace norm of this. Now, if this is Cp, that is completely positive, if and only if this is 1. However, if it is greater than 1, then the state will have some negative eigenvalues, and then this trace norm will be greater than 1. So any deviation from 1, and in the epsilon tends to 0 limit, you define this quantity gt, and integrating over all such gt, you can actually quantify the non-Markovianity. There are also some other measures of like BLP measures. That is this is monotonical relaxation of the entanglement, and whenever the monotonicity this non-monotonicity behavior is there, then you can just take it and sum in epsilon tends to 0 limit. Then you can find the non-Markovianity quantifier. Now, what is the necessary condition for uncertainty relations to hold? Robertson on his original paper showed that this relation can be derived using the property of positive definiteness of a quantum state. In 2008, Na and Jubairi also showed that positive definiteness of a state is necessary for uncertainty relation to hold. Let's visualize these things. Suppose take a state rho in some 2x2 matrix, and the positivity of rho implies that rate rho greater than 0, which is A minus C square greater than 0. Just to visualize it, now if you calculate this RS uncertainty relations for two spin-Hall observables A and B, then you will, if you calculate, and this average, if you calculate over rho, it will also reduces that A minus C square is greater than 0. So let's come to our main theorem. The theorem is a twofold. So the first one is the violation of Robertson-Schrödinger uncertainty relation for the choice state of the dynamical evolution is sufficient to detect CP indivisibility, and there always exists a set of Hermitian operator for which RS uncertainty relation will be violated in case of CP indivisible operation. So the proof is not exact proof, but just for an overview, you write the Robertson-Schrodinger's uncertainty relation explicitly, and you see that this is this term and this term is at mod square, and it is over a trace of this one, so it is a real quantity, and mods of this is a positive number, and positive, this negative makes it negative. These two terms are negative. Now if you go to that term, that the first term, trace rho a square minus trace of rho a whole square, since a is a Hermitian operator, a square is positive, and this term is also a real number, hence its square is positive, and hence this negative sign make it negative. Now if somehow this complete positivity of the dynamics breaks down, then this row contains some negative eigenvalues, and this quantity become negative. This negative, then this whole quantity is negative, and you choose operator B such that this is positive, then you see that this uncertainty relation will not hold. So negativity of trace of rho a square or trace of rho b square is sufficient to prove that uncertainty relation will be violated. However, this is not necessary, as you see that when you choose B in such a way that it is also negative, then the two negatives may make it positive, and then uncertainty relation may not be violated. So it is not necessary to detect CP individuality. Okay, then that the existence part, that the two Hermitian operator always exist. Let's write down this choice state in its spectral decomposition form. If the choice state is a Markovian choice state, then this term will not appear, this minus negative term will not appear. But if it is non-Markovian, then some lambda I plus and lambda I minus will be there, and they are corresponding eigenvalues, and hence it is right in their spectral decomposition form. The trace conservation principle yields that the sum is 1, which implies that there exists at least one positive eigenvalue to preserve the trace relations. Now if you choose A, the operator A, as the eigenvector corresponding to the negative eigenvalue, and then its corresponding projector, then you see that delta square H1 will be turns out to be negative, and you choose operator H2 accordingly that it is positive, then you see that that such kind of H1 and H2 is always exist. So recently Bhattacharya et al. Paper showed that the set of all Markovian choice states having Nilblatt type generators in small time approximation limit form a convex compact set. So based on this, we derived the following proposition that this proposition is the set of all Markovian choice state forms a convex compact set. So any state, if you calculate this relation from any state outside from this set of non-Markovian choice state, then this relation will not hold. This is actually calculated based on the convexity of the set. That is, for some observables AI and some states CM written in a convex combination of some another Markovian choice state, where pKs are greater than 0 and sum over pk is 1, and ck is within the set of all choice states having Nilblatt type generators, then this relation hold. Any deviation, that is, if the n is the CM is outside from the set of all Markovian choice states, then this relation will not hold. This proof is very simple and based on the property of the convexity. Then we will show that also for two Hermitian operators A and B, always sometime relations are better, because if a non-Markovian dynamics has two negative eigenvalues, lambda 1 minus and lambda 2 minus, you take the eigenvector corresponding to them, and you choose operator A and B such that lambda 1, the projector corresponding to lambda 1 minus and lambda 2 minus, then you see that these two terms will be negative, and hence Heisenberg uncertainty relation will not hold. However, the sum type relations will be better for this case. And here we show some examples in favor of our theory. We show, for example, from dephasing channel and spin bath model, you take the Lindblad equation, and this is actually in dephasing in Z basis, and this gamma t is a Lindblad coefficient. Also for spin bath model, this is unitary part, and there are gamma dephasing, gamma dissipation, and gamma absorption term. and we calculate this Robertson-Schrodinger's uncertainty quantity, which is red color in both two graphs, and these dotted lines are this gamma, and it's this Lindblad coefficient. You see that Robertson-Schrodinger's uncertainty only violated in those regions only where these gammas are negative. So yesterday Bielan has already introduced the witness concept of witness of non-Markovianity. Here I will like to say some few words about nonlinear witness. So you see that the set of all Markovian choice state forms a convex and complex set. Hence, any non-Markovian state which is outside the convex complex set can be separated by some hyperplane from the set of all Markovian choice states. So a operator W is said to be the witness if trace of WCM is greater than 0 for all such CM belongs to this convex set, and there exists at least one non-Markovian choice state Cn such that this is negative. And this is very simple. How to visualize it? You can take the spectral decomposition form, and this is, you see that since all pi Cm is in spectral decomposition form, then this is always greater than 0 for all I. However, if Cn is, and this is outside the set of all Markovian choices, that is this is not completely positive, then the Cn contains at least one negative eigenvalue, and the corresponding projector will be less than 0. So here we showed that corresponding to the non-Markovian witness Wi, its variance can also be served as a witness. Because you see that trace of Cn omega, this is the definition of variance, and this is positive terms. And when Cn is not completely positive, this is again become negative, and hence it can serve as a witness, non-Markovian witness. And we later we showed that the sum tabulations are always better. Finally, we propose we give the last proposition that non-Markovianity is necessary in order to decrease uncertainty for physical state undergoing unital dynamics. That is, for unital dynamics, if you want to decrease Robertson-Schrodinger's uncertainty, it can only happen if the region is non-Markovian. Otherwise, it cannot possible. So we for the proof, you write down this Robertson-Schrodinger's uncertainty relations, and the linear entropy is defined in this way: d by t minus 1 minus trace of rho square. So uncertainty in terms of the linear entropy you can write in this form, which is written in this paper by Shirai Tomal. And for unital channel, if you take this time derivative of the this linear entropy, then you can find this one, which is there in this paper by Bhattacharya et al. Where these gammas are the Lindblad coefficient, and the QIT is a Hilbert-Smith norm. So it is always positive. So this dSL by dt can change sign only if this gamma change sign. So dr by dt is proportional to this one. Again, you see that there is some constant, you can choose R and T in proper way, and this is a Hilbert-Smith norm. So if you see that dr by dt can only decrease if this is negative. The curve also shows like that only in the region of negative gamma region, the Robertson-Schrödinger uncertainty decreases. So based on this, we propose some quantifier for unital dynamics. That is, the quantifier is that, like, you take dr by dt, that is whenever, however, this is whenever the only when the Robertson-Schrödinger uncertainty is decreasing, and summing over all such things. So how much time? Okay.
Anando, you have about 5 minutes.
Okay. Okay. So I came to the conclusion section because I have.
Okay, you move slowly, but keep track of the time. That's all.
We develop a now. The conclusion is that we develop a framework for non-Markovianity detection using uncertainty relations. And we showed that for any open quantum system dynamics, violation of uncertainty relation is sufficient. However, not necessary for CPT breaking. We derived some uncertainty type relations, and violating such relations will detect non-Markovianity, where we show that the Robertson-Schrödinger uncertainty and also these uncertainty type relations based on the convex structure, and also the sum type uncertainty relations. And we present some example in favor of the theorem. Based on our approach, we demonstrate that certain nonlinear witness of non-Markovianity can be defined like variance, but we cannot say that it is improvement in some sense, because though it contains an extra negative terms, that means the hyperplane separates more so the hyperplane separates, we cannot actually conclude that the hyperplane separates more non-Markovian choice states. So there is some open possibility to find it better witness, but we just showed that variance can be used as a nonlinear witness, but we do not show anything about improvement. We also showed that for unital dynamics, this non-Markovianity is necessary to decrease this uncertainty. And based on this, we quantify this non-Markovianity. And since our approach is variance based, it will be interesting for experimental investigation for non-Markovian evaluation. And thank you very much for your kind attention.
Well, Anando, thanks for your nice talk and presenting such an interesting topic. So we have a question by Professor Aditi Sen.
Yes.
You have talked about a couple of methods for detecting non-Markovianity. So can you tell us something about the relative comparison between your way of detecting things and the existing other ones?
Sorry, just can you please repeat one more time?
Say there are other non-Markovianity measures also.
Yes, yes.
And you are defining something based on the uncertainty relation.
So there are based on divisibility dynamics. If I start to the divisibility dynamics, also there are some proposed quantifier like based on the purity, but you see that if you calculate the calculation of purity in experiment is quite harder than if you calculate just taking some Hermitian operator and you just apply the map to calculate its average on a since it is variance based, so it can be easy to do experiment.
There is another question by Shiladitya Mal. In a work by Nori et al., temporal steering is shown to be witness of non-Markovianity. Are you aware of that work?
No. Sorry, I am not.
So steering inequality of read type based on uncertainty relation.
Yes. Okay.
So I think Shiladitya Mal can directly talk to you since you seem not to be familiar with that work. So the point is that they have defined some temporal steering, so, some uncertainty relation based on the time ordered correlation. Can you make some comment on that? Whether such temporal correlation will say something about the non-Markovianity?
I cannot comment right now. I will talk to Shilajit later because I am not much aware of these things.
Okay. We can talk later.
Okay. So I have a quite awkward question that you are defining an uncertainty relation for the spin system and trying to see the non-Markovianity, whether you can detect it using uncertainty relation.
Yes.
So my question is again on the optical scenario. So let's not get into non-Gaussian stuff. If we consider only the Gaussian states and all Gaussian dynamics, so can you make some, because you are essentially using uncertainty relation in Gaussian also, all analysis is based on the uncertainty relation, or say this second order moments. So have you seen or do you plan to try something on this continuous variable part, or do you have any idea how will it help?
Uh, uh, Actually, for Gaussian state, your question is that if I am correct, your question is that how to characterize this whole things in
Yes.
Gaussian type 2.
Yes.
So the these operators, I think this uh, uh, same kind of thing. I mean, I don't know, but same kind of things also happens in continuous variables, because you just take these operators in this instead of spin operators, you can just take these Gaussian operators. So I think same kind of situation will happen. So because the main thing is that uncertainty relation, the main basic building things is the uncertainty relations, and this is also true for non-continuous variables. So I think it will work.
Okay.
Just one small comment. Somakantida, Saptarshi here. So first, if I am restricting myself to only to Gaussian states, then the usual uncertainty relations are always saturated, right?
Yeah.
So the minimum is hit. So if it is not pushed outside the Gaussian domain somehow, then whether I was thinking whether this uncertainty relations would give me something non-trivial, because I was thinking if I am only in the Gaussian paradigm, then this uncertainty relations are always hit at the stuck at the minimum.
No, that's not necessary. I mean, even within the Gaussian state, if you go for the general Gaussian, then it is not minimal uncertainty state. That happens only for the pure Gaussian state. You can always bring it to this by local operation. You can bring it to minimum uncertainty state.
Yeah.
But that's not true in general. For example, two mode squeeze thermal state you take and you increase the thermal average number of photon. It will never be minimum uncertainty state. Hold on.
Yes.
If you go for that, no,
So,
right.
so
You're right.
can
I
you
was
just
going
tell what you told that two mode thermal squeezed it, and then what you told after that?
I got it. I went to some other. I think there is one comment that for Gaussian channel, Markovian and non-Markovian distinctly have been done by Adesho and collaborators. Well, that I'll look at it.
Okay. There is.
This is a comment from Professor Shivashish Ghosh.
Okay. Well, it says like Brij Mohan and then Shivashish Ghosh. I'm a bit confused.
Brij is the moderator. He is
okay.
YouTube and gave. This is from Shivashish.
Okay. Okay. Nice talk. So,
thank you.
I think that concludes this session with his talk. So,
yeah. Thank you, Shomo, for chairing this session. And thank you all for attending this morning sessions of the YouQ-2020 second day. So we will meet again at 4:30 p.m. With the talks and also the poster presentation. Here, I just want to stress that all the posters you can actually, if you go to the schedule page of our conference website, and you can see that all the posters are the PDF of the posters are available, because in the schedule there are all the names of the poster presentation. If you click on the names, you can see the PDF of all the posters. Okay, and they will present in 5 minutes in the afternoon. And another announcement, that is after the keynote speakers talk we are planning to take every day a picture, a photo. I mean, of course, the screenshot. So please be present. So every day we are planning after the keynote talk. So thank you.